Cool. Thanks everybody for coming. So I'm Aymeric Fromherz. I'm from INRIA in Paris, and this is joint work with several people, both from INRIA and from Microsoft Azure Research. But this is a project that's especially been driven by Sean here in the room and by Guillaume Boisseau. So without any surprise, this is a Rust verification workshop. I'm going to talk about the Rust ecosystem and the fact that obviously Rust is more and more interesting for many people, including industrials, including companies, including governments that are recommending it as part of the safe coding approach. Now, unfortunately, just using Rust doesn't solve all of your problems, at least not yet, and there are many issues that remain when you write Rust programs. The first one is just a notion of panics, that is cleanly aborted executions at runtime, which might occur, for instance, if you are doing out-of-bounds memory accesses, but you don't necessarily want to have cleanly aborted executions at all. You might want to have your programs that run to completion. You have all of the standard incorrect uses of unsafe code, running from just completely memory unsafe operations to unsafe code that doesn't respect the Rust's lifetime discipline, incorrect trait implementations. I'm thinking, for instance, of unsafe traits claiming that they unsafe types claiming that they implement send or sync when they do not, broken invariants that are required for safely using unsafe code, all of that jazz. And obviously also the standard functional correctness issues where you wrote some code, but unfortunately it doesn't do what you expected it to do. So all of this means is that despite Rust bringing something to the table compared to C and C++, there is still a lot of room and a lot of need for formal verification tools. And when I'm saying there is a lot of need, there actually are many diverse applications, many diverse properties that you might want to have, which led the way to many different tools that have been developed. So you have a whole range of unsafe code analyzers. So for instance, stuff like Redra, which is testing for some memory safety issues in unsafe code, Yuga that does some lifetime analysis, some recent papers about Borrow Sanitizer. You have some more specific, domain-specific analyzers. So to give you an example, there is this Clint tool which is really focusing on atomic contexts inside of kernel code. There is a new paper about RAust which does some resource analysis in Rust. And then you have also the plethora of deductive verification tools, many of them being presented here today, Eneas, Creusot, various Prosty, and so on, which allow you to derive very strong properties, especially about the functional correctness of your Rust programs. Model checkers, symbolic execution tools such as Canny very fast, and other tools that are not necessarily directly related to verification, such as transpilers, including the EuroDC transpiler. So the whole point of this is that we have a very, very rich ecosystem, and I would argue that this is actually a good thing. First of all, it's a good thing scientifically because it's a good thing to explore different approaches to Rust verification, but more importantly, it's a good thing for the Rust ecosystem because you really want to pick the tool that solves your specific problem, and as much as possible, you're going to have trade-offs between, say, automation and expressiveness of the tools, and so you want to pick the tool that best suits your needs. Now, how do all of these tools work? Well, all of these tools are going to have to interact with the Rust compilation toolchain. So the Rust compilation toolchain, it's a pretty standard toolchain. If you start from some Rust code, you're going to go through the Rust C compiler, and in the end, you're going to get some executable code. Now, let's say we want to write a verification tool, say Eneas. What we're going to do is get one of the intermediate representations of the Rust C compiler, get somewhere in the middle of the compilation toolchain, extract all the information we need, and build a verification tool that's going to operate on this internal representation, and therefore allow us to analyze, to verify a generic Rust program. Now we do this for Eneas. There comes another tool, say Veris, which is going to do the same thing, operating with the same Rust C compiler. And yet another tool, and yet another tool. So the whole point here is that whenever you're going to have to write a Rust verification tool, you're going to have, in some way, to interact with the Rust C compiler. And as some of you might know if you have written compiler drivers, this is something that can be challenging for different reasons. The first one is that the Rust C compiler is, well, it's a great compiler, but it comes with a very large, complex code base and with many, many internal details, many internal representations, many internal APIs to know, which might be hard for somebody that just wants to come into it and maybe write a very simple analysis. And this is a compiler which is really optimized for compilation and for speed of compilation. And so what this means is that it comes with a design which is centered around compilation, where, for instance, you're going to have to query the compiler to retrieve some semantic information, because depending on the compilation passes that you are implementing, you might not need all of the semantic information at any point. And there are also some things such as the steal abstraction, which provides you a pure view over mutable data structures, which helps with the speed of a compiler, but which means that, for instance, if you are querying some information, the steal abstraction might kick in and might invalidate your current representation, and therefore you won't be able necessarily to query again the compiler on the same representation, which for analysis has another overhead in terms of the knowledge you need to interact with a REST compiler. And so, in addition to these queries, what this means is that you're going to have queries at different points, and the information you're going to need for semantic analysis, the analysis-relevant information, is going to be scattered throughout the code base and scattered throughout different queries. And so retrieving all of this is going to be quite tedious and time-consuming, and can be a bit of an overhead for newcomers that just want to develop new tools. And obviously, this is just about interacting with the REST compiler itself, but if you want to analyze REST projects, you're going to have to interact with the broader ecosystem, and especially cargo, which comes with yet another challenge in terms of the effort you need to provide. So, as part of the development of, yes?
We would have to discuss the documentation is one of our completely missing.
Yes, I'm not claiming this is an exhaustive list. I'm claiming that already these things are painful enough that if we can avoid doing this, we would very much like to do so. And so that's why, especially when Sean was initially developing NAS, we have been asking the question of, is there anything we can do better? We want to write new tools, we're going to have to redo this work all the time. We don't want to redo this time, we want to develop new tools. And so this is what led to the development of Charon as a standalone platform. And so the whole idea of Charon is that instead of having each tool that goes directly into the internals of a REST compiler, we're going to have some common abstraction layer on top of the REST compiler. And so the important part here is that Charon, it's really intended as an analysis-oriented interface into REST-C. It comes with different trade-offs. It doesn't come necessarily with the speed of a REST-C compiler, but in exchange, it aims to make it easier to develop new tools, because you're going to have all of your semantic information available in one place without needing to dive into the REST-C internals. And so we really hope for this to be a collaborative effort around projects, because this is something that works for us and that works for more and more people right now, but this is something where we see value for most tool developers to avoid the tedium of going through the REST-C compiler. So before diving into some technical points about Charon and how Charon works under the hood, let me give you a quick overview of the workflow. So let's say we want to analyze a REST program. The starting point is going to be the REST-C compiler. And so REST-C compiler itself, as many compilers, it has several intermediate representations internally. And so in particular, you have here the high-level intermediate representation, here a type version, and then mir, and then you go all the way to LLVM for code generation. Now, as part of Charon, our choice was to start from mir, and this for several reasons. The main ones is that all of the semantically relevant, semantically important information is available in mir. And so I'm thinking about moves, about copies, about borrows, reborrows, two-phase borrows. All of this thing is made explicit in mir, which if you want to develop semantic information, semantic analysis is extremely useful. So what does Charon do? It interacts with mir, it takes the mir representation of the program, and it extracts it to a cleaned up version that we call ULLBC, which retains the control flow graph methodology, the control flow graph representation of mir. Then, on top of ULLBC, we have several cleanup passes that are implemented, most of them being optional, which aim to make using ULLBC, using this representation, more palatable for tool developers. Additionally, for some examples, it's sometimes more useful to have an AST to have a structured representation of a program instead of a control flow graph. So we have, as part of Charon, a path that performs control flow reconstruction, and I'm going to talk a bit more about it a bit later, and which translates ULLBC to LLBC. The U in LLBC meaning unstructured, low-level Borrow calculus, and so therefore here we have structured or just low-level Borrow calculus in LLBC. And so these two representations are going to be what is going to be consumed by tools, by verification tools. And so I'm going to show a bit more examples in a minute, but here this is going to be some kind of abstraction layer on top of rustc so that tool developers do not need to see anything about rustc. Now, all of this is just for interacting with the Rust compiler. Obviously, if you want to interact with Rust projects, you're going to have to interact with the cargo ecosystem. And so the way, if you were to just develop a Rust project, you would type cargo, have your cargo.toml, which defines your project. You're going to have the same thing, but you're going to have Charon that takes care of it for you. And so instead of calling cargo at the root of your project, you're going to call the Charon executable, which itself is going to call cargo, which is going to call the Charon driver, which is going to call the rustc compiler. And so in the end, all you will get is just cargo Charon at the top level, and you will get representations in ULLBC and LLBC of your project. So let me now dive a bit into some of the specifics and some of the internal details of Charon. Why do we need Charon, and what are some of the cleanups and the simplifications that Charon is doing? Well, one particularly telling example is how Charon simplifies the representation of constants in rustc. So in rustc, and especially in Mir, constant values have a very low-level representation. And what I mean by that is that in many cases, the constants have been evaluated already, and you just have an array of bytes that are laid out, which is going to be what's going to be compiled in the end. But if you want to do a semantic analysis, it might be useful to have a more structured representation to know what kind of constant you are actually using. And this part about the representation is just one of the complexities of using Mir for constants. You also have a separation in types between constants used in types such as for const generics and other constants. And what this means is that retrieving the high-level representation of a constant, the one you had written in the original source code, can be tedious and requires calling a bunch of rustc helpers, which are going to depend on the current type of a constant, and so on and so on. And so if you want to do it for, say, ADTs or enumerations, you're going to have to do this recursively, and that's going to be not only error-prone, but also quite annoying. So what does Charon do? Well, Charon does that once and for all for you. And so instead of having to interact with arrays of bytes laid out, it just gives you this kind of high-level representations, where here the ADT case is just one of a case of the different constants that are available in rustc. But you can simply interact with this and have access to a high-level reconstructed version of a constant. And so the example of constants is particularly telling, at least to me, because at a high level, I'm thinking of a constant as just some value that I see in my source code, but Charon is also performing many other reconstructions, such as removing the steel abstraction that I mentioned earlier, but also transforming some low-level switches over discriminant into more high-level standard matches, the same way you would have in high-level code, things like that. And some of these passes are also optional, so that depending on your needs, you might want to enable them or not. So what are some of the other things that Charon is doing for you? Well, one of the main things is also reconstructing partial or missing semantic information in the compiler. And to explain this, I'm going to rely on this very simple example, this very simple Rust function, which is performing a clone on a vec. So if you compile this with rustc, at the Mir level, rustc is mostly going to be focusing on showing that it is valid to call clone on the value v. And so to do that, it needs to show that v, the type of v, indeed does implement the clone type. So it's going to say it's a vec of t. It's going to say, OK, vec of t implements vec if t, vec of t implements clone if t implements clone. Oh, there is a t clone clause in the while clause, then we're good. But Mir only cares about the existence of a trait instance satisfying the bounds. And so in particular, if you want to analyze it, you might care about saying, I do not just want the existence of a trait instance, I want the specific trait instance that's going to be available here to know which trait instance to analyze. So in this case, this is just going to be the one in the T clone, but in other cases, when you have more trait bounds in the where clause, when you have super traits, implied trait bounds, it can get more and more complex. So how to do this? Well, the workflow, generally speaking, is first of all, internally, you have to query the trait solver to get as much information out of rust-C as possible. And so this already comes with some challenges, also related to documentation, but challenges related to how do you handle binders for different lifetimes, trait clauses, and so on and so on. So it's something that is quite complex. And then once you retrieved all of the trait information you could out of rust-C, you need to reconstruct the complete trait instance, reconstruct the missing or partial information in the presence of where clauses. And this is going to be something operating on the where clauses and reasoning about implied trait bounds, super traits, and so on and so on. So the good point is that, once again, all of this is done for you in Charon, and that's something that required about 600 lines of Rust code. And don't look too much at the actual representation, but the important part is that all of this information is part of the ULLBC and LLBC representations that are provided by Charon. And so if you just want to analyze a program, you do not need to redo this work. Yep.
I'm just wondering that you say at the MR level, this specific trait instance used is not evident in the representation. That suggests that it would be computed by some later phase in Rust-C.
Yeah.
And then it sounds like what you're doing is trying to reconstruct what that later phase might do by calling the trait solver and so on.
Sean, you wanted to say?
So one issue is that actually there is no things about Rust-C which gives you this exact optimization. The reason, one reason being that they don't need to. They only need to find out which implementation you're using when they are modifying the code. So there's nothing which can support actually this is here in this generate function we're using the principles.
So I wonder, like, is it a concern that in a subsequent monomorphization class, the decision that the Rust compiler makes might be somewhat different than the decision that that Charon makes now?
It might be the same code that is called to make that.
Could be the same code, but it's a complex piece.
Yeah, it's as of today it's okay. It really depends on how the Rust documents are very well with regards to specification. Maybe we can do some later. As of today, it's okay. It really depends on feature estimation to the process.
Yeah. So I think, indeed, this can be a concern, but we are trying to take as many steps as we can to avoid this. And at least we believe that this would be a concern anyway for other tools trying to redo this work. And we see value in trying to do it once and for all and trying to get only one tool to agree with what the Rust-C compiler is doing. Yeah, but thanks for your question. Okay, so beyond simplifying representations, beyond reconstructing semantic information, one of the last important things that Charon is doing is interacting with the cargo ecosystem. And so, as most of you might know already, the main role of cargo is to handle dependencies, to fix dependency versions, to handle the build system, specify build options, basically provide you with a convenient framework, a convenient reusable framework for building your projects. And so, as I showed earlier in the workflow, Charon directly piggybacks on top of the infrastructure, of the cargo infrastructure. And so what this means is that, as for several tools, running Charon is as simple as calling Charon cargo at the root of a project. And so this will extract the entire project. There are several options that are available in Charon, and I will talk about it a bit more during the demo. But the whole point is this is intended to be as simple to use as possible for people that are already used to the Rust ecosystem. Now, most of what I was mentioning was related to ULLBC, which performs all of these cleanups from mirror and tries to reconstruct the information. In order to also help with some analysis, we have this other representation called LLBC for low-level Borrow calculus. So the whole idea is during the mirror to ULLBC translation, we want to stay as close as possible to the original code, and therefore we want to preserve, for instance, the control flow graph structure that is available in mirror. But because on some cases we want to have a structural representation, and one telling case, for instance, is if you want to have a transpider from Rust to, say, C, you're going to want to have some actual structured code with if and else's, with loops in the end, then it is nice to have a structured representation which keeps this control flow. And so there is a control flow reconstruction pass in Charon, which is preserving all of the semantic information that was available in Mir and therefore in ULLBC. So all of the things about moves, copies, borrows, all of that. And this reconstruction is pretty much best effort. We cannot guarantee that it will give you exactly the Rust code you had at the beginning, but it is inspired by standard work on the relooper algorithm in particular, and there are many heuristics which aim to get it as close as possible to the original code. Now, if what you're mostly worried about is how do I actually use Charon, Charon is exposing several APIs for ULLBC and LLBC as a standalone crate. And so what this means in particular is that if you want to use Charon, you don't necessarily need to handle all the Rust C dependencies, and so therefore this is something that we aim to simplify the use of Charon by downstream tools. And we also have some JSON serializers for both ULLBC and LLBC, which allow analysis to be developed in other languages. All you have to do is say if you want to use Python for interacting with Rust C, you would have to write a deserializer for Python and have a representation of ULLBC and LLBC in Python, and this would allow you to develop new analysis in Python. And this is actually something we are doing with OCaml, because for some of the tools we are developing, we like writing them in OCaml better for different reasons. But so we have a complete library on top of Charon, which allows you to have access to ULLBC and LLBC inside of OCaml, and therefore build new tools interacting with Rust in OCaml. So a quick disclaimer about the current state of Charon. We are quite far along in terms of how many features we support, but there are still some things that are yet unsupported. We have a plan to support them in the next month, hopefully. But to give a full picture of this, some of the unsupported features include the Dean trait, generic associated types, which are a bit more complicated to handle than the regular associated types, async, and also where precisely the drops are. And the main reason for this last point is that at the moment, we are interacting with Mir builds, but there is some ongoing work to use some later Mirs so that we can have more semantic information directly out of Rust C. So this is work that is planned that we intend to do in the next few weeks or few months, depending on the work. And importantly, even for the unsupported features that we have at the moment, Charon is by design intended to be robust. And what I mean by that is that the tool is not going to just crash at the first unsupported features. It's going to try to extract as much as possible from your project. So if you have a feature deep inside your code that is not supported, it will introduce some kind of hole or implement it. And if you have a declaration that cannot be translated for different reasons, it will just skip the declaration, but translate the rest of the crate. So this is a high-level picture of Charon. Let me also try to show you a bit of how Charon can work. Oops. Okay. So let's start with the shape of a Rust code here. This is just going to be a somewhat simple code, but hopefully it will be able to demonstrate some of the features that Charon provides you. I can try. I could have tried. Let me try it with Emacs because I know. Yeah. Okay. In any case, the specifics of the code are not necessarily the important parts. This is somewhat standard Rust code. You have some notions of lifetimes. You have some notion of mutable borrows. You have some if-then else's here. So for instance, this is a standard choose function where you just take two mutable borrows and you return one of the two depending on the value of a Boolean, which is also passed as an integer, as an argument. And so if I run Charon on this, I can do this, for instance, with the print ULLBC version. So here the syntax, if I want to do it on just one single file, is going to be to query directly rustc instead of querying cargo. And so I'm going to print it in a way that is going to be more readable into the demo print ULLBC file. And so now, if I look at the ULLBC file, what you can see is like cleaned up, a pretty printed representation of the ULLBC representation of the different functions. And so in particular for this choose function, you have access to the signature of a choose function, including the arguments of the lifetime and the type. You have a list of all of the local variables in the function. And so a convention that we have is that the first one is the return variable of the function, then we have a list of arguments, then we have the actual local variables of the function. And then what you can see here is the control flow graph representation, where you have a bunch of blocks, and at the end of them, either some go-tos or some conditional go-tos. Okay? And so you have this for pretty much all of the functions in this example. Now, yeah, so storage live and storage dead is some internal Rust stuff where basically you have local variables that appear at the top of a function as like the list of all the local variables, but they are not necessarily allocated at all times because maybe you're going to need a local variable pretty late in your function. And so there is this storage live and storage dead information in the Rust compiler, which actually represents when are these variables available. So this is also something that we are propagating and that we are making available as part of the Charon representations. Yeah. And so if I do the same thing, but instead of print ULLBC, I'm going to here print the LLBC code. You're going to see pretty much the same code. So let me put the other one on the right. And so here, if I look in particular at choose, you can see that the two pretty much match, except instead of having this control flow graph representation, you have a cleaned up version with if then else's on the left. Okay? And this is something, if I go back to the actual Rust code, that also works with more complex control flow. So without going into the actual details of what this function does, all this does is just taking the nth element of a list by looping over a list. And so if I look post control flow reconstruction, you can see that you have both this loop here and also a reconstruction in terms of higher level ML style matches instead of matching on low level discriminants. And so again, the specifics of the code itself doesn't matter too much. The important part is this is something that is available directly if you use Charon for analyzing and translating this kinds of program. Now, in addition to this, I can also try on a full crate. And so the way I'm going to do this, just for the sake of time, I'm going to do this on a very simple crate, which I'm not sure if you can see it, is called simple slab. But so if I run Charon cargo on this and ask it to print the LLBC, it's just going to compile the crate and outputs this LLBC, which contains all of the information of a crate. And again, the actual information is not important. The important part is that just doing Charon cargo gave you all this information. And so the reason why I was using this print LLBC option is that otherwise you just get the serialized version of all of this, which is, at least as a human, much less readable, but you can implement deserializers easily if you want to use something else than Rust or OCaml to interact with this. Now, I was also mentioning some of the options that we have. Oops. Without getting into too much details, the important part is we have several options that allow you to parameterize how you want to interact with the extraction. And some of the interesting ones are especially this thing, this include here, as well as the exclude and opaque versions, which allow you to provide patterns of the functions of the declarations that you are interested in extracting. So if for whatever reason, for instance, you do not want to have your entire crate extracted, you're only interested in a subset of a crate, a subset of your project, this is something that you can do with this kind of include-exclude options and a name matcher that is implemented as a part of Charon. Okay. Coming back to our presentation, I want to conclude today by talking briefly about some of the applications we currently have about Charon, so that I can try to show you that this is something that is already usable. So one of the small ones that we have is a prototype of a taint analysis. Just to give you a bit of context, why do you need a taint analysis and what is it? The whole idea is that for several kinds of security-sensitive code, especially cryptography, that's the kind of code that typically operates on secrets. So if you're thinking about cryptography, you can think, for instance, about secret data or cryptographic keys. Now, the issue we have is that it's not sufficient for these kinds of applications to just write them correctly. You also have attackers that can infer the secrets just based on observations about the execution of a program. And so that's something that's going to be called side channel attacks, if you're familiar with term. And so to give you a bit of a toy example, suppose that we were to implement a function that verifies a password, and suppose that we were to implement it naively by saying, if I try to check whether message matches password, the first thing I can do is check if the two are of the same length. If they are not, I know already that the password doesn't match. And otherwise, I'm going to check it character by character. Now, the issue I have with that is that the execution time of this function is going to differ depending on the password I am trying to check. And so in particular, for an attacker, you can try many different passwords, and first of all, just by timing the different execution of a program, infer what is the length of a real password, and then infer it character by character. So that's a typical example of side channel attacks. What's the solution to this in cryptography? This is something called constant time programming, where the whole idea is that cryptographic code should rely on a constant time programming discipline, where you are forbidden to either branch or to access memory based on secrets. So branching, this is obviously for execution time. Accessing memory, that's for some execution times that are related to the cache patterns. But that's a bit out of scope for today. Now, how to ensure that? Even if it seems somewhat simple enough, that's something that has been error-prone, especially recently. And so a common solution is to have a small static analysis called a taint analysis. And the idea behind taint analysis is that you're going to taint at some attribute, at some annotation on your initially secret data, and you're going to propagate this taint throughout your program. And then if the taint, for whatever reason, appears in a place where it's not supposed to, this means that you are either branching on a value which might contain some secret information, or accessing memory based on a value that might be containing some secret information. So this is something that we have a prototype of on top of LLBC in Charon, and it relies especially on annotations in the source Rust code, such as, for instance, saying if I have a function, I can specify that the two arguments key and a are supposed to be tainted or supposed to be secret. And these annotations are also propagated by Charon all the way to ULLBC and LLBC, which allows you to leverage them for further analysis. And so this analysis itself, again, it's a prototype, but it was implemented in about 1,000 lines of OCaml, and it was sufficient to run on several existing Rust cryptographic implementations, including a part of the Hacklestar cryptographic library, a new verified library called libcrux, and also several small parts of Rust crypto. And so the important part is that this is a bit bogus because we already knew the existence of this vulnerability, but the analysis was able to rediscover a recent vulnerability on post-quantum implementations called Kyber/. Now, to finish the tour of some of the other applications we also have a part of the RUDRA static analyzer that we have done on top of Charon. So what is RUDRA? This is a recent third-party Rust static analyzer. It's not something that we have developed. It's a completely separate project, which mostly targets analysis of unsafe code and especially unsafe memory safety bugs in unsafe Rust, as well as some incorrect implementations of the send and sync threads. So RUDRA was, as pretty much all of our tools, interacting directly with Rust-C. We ported it to use ULLBC instead, and it was actually quite fast. The complicated part was the analysis itself, but replacing the internals of Rust-C by just using ULLBC, this required about a day of work for the memory safety part. And interestingly, porting the send-sync part analysis. This was done by somebody completely different that is not related to us in any way, and they managed to do it as well reasonably well. The last, one of the last case studies I want to mention is the Eurydice transpiler. And the idea is that even though you have more and more projects that are going towards REST, you still have some clients that, for whatever reason, wants to have C code in the end. And so we love REST because it simplifies our life for verification. But if people are not interested in REST code and want C code in the end, we need to have a way to provide this. And so this is the main purpose behind Eurydice, which aims to translate a subset of safe REST directly into C code. There are some technical details that are needed to do that. I don't want to get into the technical details themselves, but the important part is that this is something that allows you to develop and verify code in Rust, and then extract it to C and deploy C code for the clients that need it. And so this is something that is built on top of LLBC, and for the translation, the most important parts where we needed to have an explicit, the semantic information that was explicit, especially about moves and copies, so that we could put them into C. We needed to have the control flow reconstruction so that we could generate idiomatic C code, and we also needed precise trait information to translate traits to actual C functions. The fun part is, beyond all of these static analysis tools, you can also run Charon on Charon itself. Why would you do that? Well, the main reason is that it's also simplifying our lives for maintaining bindings. If you want to maintain bindings into ULBC and LLBC for different languages, if the representations change, you need to propagate all of this. This can be quite tedious and quite time-consuming, and we would very much not like to do that. So instead, what we can do is run Charon on Charon to get all of the definitions of LLBC and ULLBC, and then have a small program that automatically, out of this representation, generates all the information we need, such as the type definitions here in OCaml, as well as visitors, deserializers, basically all you need to consume ULLBC and LLBC in other languages. And additionally, again, leveraging Charon's support for Rust attributes, we can put some custom attributes in the original Charon Rust code so it can have some finer control on what the shape of the OCaml code looks like. And especially this is something that we need to remove some name clashes, because in OCaml you cannot have two structures or two types, for instance, with the same constructors. Other Charon uses I want to briefly mention. The first one is obviously our flagship project, Aeneas, that Sean is going to talk more about later today, so I don't want to spoil his talk. But it's also some new analyses that are being developed on top of Charon. And one we accidentally heard about was Array Rest, which I think was just accepted to Uppsala, and which is a new resource analysis for Rust. And so what this seems to suggest to us is that Charon has the potential to reduce the effort for developing new analysis, especially for instance, students, academics, people that do not necessarily have all of the engineering manpower to directly go and interact with Rust compiler. And so the important part is also we are hoping that several parts of Charon can be reusable beyond using all of Charon. And so as far as I understand, the control for reconstruction has been integrated in the Canny model checker developed at Amazon. So what's going on and what's left? Well, the first thing is obviously we want to get to a point where we can translate pretty much all of Rust. And so we are actively working on supporting the remaining Rust features. We have internally a tracker which is run weekly, which runs on the Rust C-test suite, which allows us to understand where we are at concerning the Rust features. And we are hoping to do an alpha release of Charon in the next few months so that we can have something stable and usable as much as possible. We are developing ourselves some novel analysis on top of Charon, especially targeting some security critical and unsafe code. And my personal ambition with Charon is really for it to be a collaborative effort and a basis with many building blocks that can be tedious to re-implement that many different tools or analysis are going to be using. And so, for instance, reasoning about places, perhaps having a dominator analysis, perhaps having a points to analysis for unsafe code. These are the things that, for instance, are really helpful in LLVM and that I hope we can get inspiration from for something like Charon for the Rust ecosystem. So to conclude, the main takeaway is that we have a new tool developed, Charon, which is really intended as a collaborative effort for having a framework for developing new Rust semantic analysis, being full-fledged deductive verification tools or shorter, smaller static analysis. And all of this is available on GitHub. It is open source. We pretty much welcome PRs, pretty much welcome issues, contributions. If you are interested in any of this, we are also on Zulip, so don't hesitate to come, join, and talk with us. And with that, thank you for your attention.